Okay, class, this is a continuation of the membrane processing discussion. I was cut there, so I will just continue with, I think this is the second to the last membrane separation process, which is gas diffusion in a porous solid. So a microporous solid membrane separates the two gas phases in this case, and these gas phases are present in both sides of the membrane. The rate of molecular diffusion of the various gas molecules here depend on the pore size and the molecular weights. Now, separation of gaseous components is achieved using the membrane now has these selective properties. So it will only select that particular gas molecule that will pass through it. When the pores are much smaller than the mean free path in the gas phase, about 1000 angstrom at standard conditions, the gas diffused independently by the Knudsen diffusion. Now let's look into the manner in which this particular gas molecules diffuse through the membrane. Now, in Knudsen diffusion, as you can see here, you have the feed here, and you have these membranes, and the permeate is able to pass through the membrane. So, the permeate are the ones, or those molecules that passes through the membrane and are already on this side, while the others remain on the other side of the membrane. So the driving force in this case is the pressure difference or the potential difference on the sides of the membrane that allows those particular gas molecules that the membrane will allow to pass through to pass with ease because of this driving force. And that is in the case of gas diffusion in a porous solid. Now, application of gas diffusion in porous membranes include the production of enriched uranium by forcing gaseous uranium hexafluoride through a semi-permeable membrane. And that particular semi-permeable membrane is this membrane in the illustration. So you have the natural uranium here, which is 0.711% of the uranium isotope 235. Now, what you have on the other side are the enriched uranium and the depleted uranium tails. So, this is just one of the many applications of gaseous diffusion in porous membrane. Now, there is the mention of the mean free path for a gas molecule. And in your chemistry 1, this was discussed that the average distance a gas molecule travels before it collides with another gas molecule is this particular mean free path. So on the average, how long will a particular gas molecule travel before it collides with another? And it's a function of the viscosity of the gas, its pressure, its temperature, and its molar mass or molecular weight. So you have the mean pre-path is as represented by this Greek symbol, and it's in meters. Viscosity is in Pascal seconds, pressure is in Pascal, temperature is in Kelvin. Your molecular weight is in kilogram per kilogram mole, and you are to use this particular universal gas constant. So please take note of the formula in determining the mean free path. Now, in terms of determining the diffusivity of a gas through a membrane with the unit of square meter per second, it's now dependent on the average pore radius of the molecules of the gas and the average molecular velocity for the component A, and that is in meters per second. So this is the formula for that. Another alternative formula is in terms of the average pore radius still, but this time we take into account the temperature of the gas and its molecular weight, and this particular formula is based upon the kinetic theory of gases. But still, it's able to evaluate the diffusivity of the gas. Now, all the variables that appear in the two formula here are defined on the specific lines below the said formula. Now, the last membrane separation process is the liquid membrane. So it it involves a combination of solvent extraction and stripping processes in a single step. And if you recall in the previous discussion, even if it's a case of a membrane separation process applied to a gas, there is at times this particular optional liquid or gas that is added. So it's a solvent actually that is being added on the permeate side so as to create shall we say, a gradient, in that case a concentration gradient that would ensure the separation of your desired component from the rest of the components in the mixture it is contained into. Now in the case of the liquid membrane, so you have your feed here, and these are your membrane porous support, and this is your receiving phase. This side is the receiving phase, now flowing in the direction opposite to that of the feed. And this is your liquid membrane, and you have the liquid membrane being supported by this support, which are porous as well. Now application of liquid membrane includes recovery of zinc from wastewater in viscose fiber industry and recovery of nickel from electroplating solutions. Now what are the problems that are normally occurring or commonly encountered problems in membrane separation processes? Now, since we are using a membrane or a barrier that will allow the separation of a component from the rest of the components in your liquid or gas mixture, potential fouling is expected in the membrane itself. So there's a need for cleaning of the membrane, or if there is a way of regenerating the membrane, or ultimately change the membrane. So maintenance in terms of properly checking on close time interval the status of the membrane should be ensured. Now another problem is solid present in the liquid feed. So as I have mentioned in the start of the slide, our feed are most of the time homogeneous, or shall I say miscible. And if solids are present in a liquid feed, then it is something to be considered, because that makes it then not totally miscible because of the presence of the solid. And of course, I have mentioned already, related to the first one, the concern about the cleaning of the barrier or the membrane. Okay, so thank you for listening on this particular type of separation process. This is the last already, and hopefully if you have questions, you keep me updated in our Canvas or even through our GCs.